Hello everyone, welcome to BHARGAV SUBS. So in today's class, let us discuss the theorem regarding equation of continuity of current. Right, what is this equation of continuity of current says? It says the charge will not appear or disappear spontaneously. Okay, on the spot it doesn't like appear or disappear. It will flow continuously, either inwards or outwards. Like there is a continuity of current while the charge was flowing. So current is in the form of charges, right? So charges flow either inwards or outwards continuously. So for that there is an equation which represents the charge flows continuously. So we will discuss the equation for that, right? So equation of continuity of current. Okay, for this, so like for bringing this equation, we will consider a conductor where the current flows continuously, like the current is flowing. So I am considering a conductor. So this was the surface, like ds. Now a current was flowing I, right? So here the current was flowing, no, like there is a current density J. So J represents current density. I represents current. What is this represents? Surface integral, right? Surface integral. What this represents? Volume integral. What is this represents? Charge, Q. What is this represents? Rate of change of charge, right? So now the current was flowing inside, right? Now what I have to take, see the current, like the J is the rate of change of current flowing through this surface ds, right? Rate of change of current is flowing through the surface ds. This was the J, current density. Current density can be represented as di by ds. Okay, rate of change of current flowing through the surface. Now di can be written as J into ds. Okay, J into ds. Now what I am doing, I am applying integral on both sides. So di is equal to, here ds there, no, so surface integral J dot ds, right? So like this integral differentiation will cancel. So I is equal to surface integral J dot ds, correct? So this was the first equation. Now according to divergence theorem, okay, according to divergence theorem, what we have according to divergence theorem? We have surface integral J dot ds is equal to volume integral gradient of J dv, correct? So this was the 2. So I can substitute here 2 in 1, right? So I am substituting 2 in first equation. What I am getting? I is equal to what is, like I am substituting, like in the place of surface integral I am substituting volume integral. So volume integral gradient of J dv. So what is the current is? What is meant by current? Rate of flow of charge. Current is nothing but rate of flow of charge. So this was like current was moving, means charge is also flowing. Now there is a decrease in charge, correct? While it was flowing out, like in the conductor there is a decrease in the charge, right? So like what is happening? Negative charges decreases, okay, positive charges increases, right? Negative charges is going out, positive charges increases. So I is equal to, I can be written as minus dq by dt. Okay, there is a decrease in the charge, so I can substitute in the place of I can substitute minus dq by dt. Okay, so this is substituting here, right? So minus dq by dt is equal to volume integral gradient of J dv, correct? Now up to here, okay, this was the third equation. Now you know, like charge can be written as rate of change of charge density. Like here charge, like through the volume, okay, through the volume through the some volume rate of like volume integral of charge density, like total volume integral of charge density is equal to the charge present inside the conductor. So I can write charge can be a volume integral of charge present in the conductor. So minus d by dt of, right, charge can be written as volume integral charge density, okay, with respect to volume dv is equal to volume integral gradient of j dv. Charge I wrote like this. So minus d by dt rho v dv volume integral is equal to volume integral gradient of j dv. Now see here, on comparing on both side, what I get, the volume integral dv. So I can write minus rate of change of charge density is equal to gradient of j, correct, gradient of j is equal to minus d by dt. So I can write gradient of j plus d rho v by dt is equal to 0. So this was the equation of current, okay, this was the equation of current. How I can say this was the equation of current? For example, charge is flowing in. So what it means, like charge was increasing. So if charge was flowing in, charge was increasing, see, rate of change of current density, like charge was flowing means charge increases inside it. So what you will get, this one, what you will get, like it was positive, greater than 0, okay, then what you will get, rate of change of current density less than 0. See, so first case 1, if charge density increases, okay, if charge density, this was increasing, so like delta gradient j is equal to minus d by dt of rho v now. So if charge density increases, what it means, d rho v by dt is greater than 0, okay, it was increasing, so differentiation is greater than 0. So if I substitute positive here, positive into negative is negative, so delta j is negative, okay, what it means, like delta j, gradient j is negative, is less than 0, okay, less than 0 means like it was flowing out, like current, like charge was flowing outward, right. So it means charge is flowing outwards. Now second case, what is the second case? If the current density decreases, correct. So if the current density, case 2, if current density decreasing, so if current density decreases, then d rho v by dt is less than 0, correct. So j is equal to minus d rho v by dt now. So it was less than 0 means negative into negative, which was positive, okay, gradient of j. So it was positive means like the current density is increasing, so it means charge is flowing inwards, so inwards to the conductor. So case 3, what case 3? If charge density remains constant, like if charge density is equal to 0, then, so if charge remains constant in the conductor, so then what is the differentiation of constant? 0, d rho v by dt is 0. What it means, like charge is neither flowing inwards nor flowing outwards, okay, like charge remains constant, charge inside remains constant. So finally what it says, it like charge is like neither appearing or disappearing spontaneously. It was continuously flowing, like it is flowing inwards here. Charge density flowing inwards. Here it was flowing outwards. Okay, so what is it called? Like gradient J, no, this is nothing but net flow of charge. Okay, net flow of charge outwards. Okay, so like net flow of charge outwards means like we got this was negative. Okay, means the charge was increasing inside, like flowing the charge outside we got negative. Okay, like it means it says the charge is flowing inwards, right? Here I got charge like net flow charge outwards positive, means it is flowing outwards. Okay, we got positive net flowing charge of gradient of current density is nothing but net flow of charge flowing outwards, it means. So if we got that one is negative, then what it called? The charging flowing inwards. If you got this one positive, what it called? Then it was flowing outwards. Okay, positive means it's like positive response. So you got charge is flowing outwards, right? Yeah, that's it. So this is the equation of current. What are the units of like charge density and current density? Units of charge density and current density. Charge density unit was ampere per meter square. Like current density was coulomb per meter cube. Okay, these are the units of charge density and current density. Yeah. Thank you.